Hi there, this is Professor Shannon Gracie. Today we will be covering section 5.8, which covers exponential growth and decay models, Newton's law, logistic growth, and decay models. Um, we are working out of the Sullivan and Sullivan text pre-calculus enhanced with graphing utilities, and I hope that you're having a fabulous day so far. So let's get started with a warm-up, which has us graph these two exponential graphs, right? So what do you think is going to happen with these graphs? Let's see if you're right. Okay, so our first one was 500 times e to the 0.02, and we'll use x instead of t. And the second one was 500 times e to the negative 0.02 times x. All right, let's check them out. So that's not very illuminating. Let's just go to Zoom standard. Oh, we have 500 as a multiplier, my bad. Let's see. Let's go to, we'll go to Zoom Fit. There we go. So that's not giving us a big idea of the curve. Um, so I'm going to take a look at the window. $409 to $610. Maybe if we do the Y scale by 50. Let's check out that graph. Just doesn't look very exponential. I see a little bit of a bend, but I think we need to do our window. Sorry, there's my dogs outside. There we go. That's going to look a little more curved. Maybe we need to go further on the X. So let's do X from negative 20 to 20. See what that looks like. That's going to be good enough. All right. So it looks to me, so this one here was the first graph because it's a, it's a growth function. And so this is A at t equals 500 e to the 0.02t, and this one here is the decay function. Okay, so how do they look to be related? What do you think? Are they reflecting across the x-axis? Nope. How about the y-axis? That's what it looks like to me. So A at t equal to 500 times e to the negative 0.02t is the graph of A at t equal to 500 e to the positive 0.02t reflected across or about the y-axis. All right, so let's check out this exponential growth and decay, these models. Now, the cool thing about these models and the confusing thing about these models is they use different, notation, but it's really all the same thing. So if you do A at t is equal to A0, some initial amount, times e raised to the k times t, you're going to see n at t equals n0 e to the kt. You may see p at t equals p0 e to the kt. It's all the same. Now, if k is positive, you're going to have a growth function. If k is negative, you're going to have a decay function, all right, like we saw in the warm-up. So let's write that down in words. If k is greater than 0, the function models the amount or size of a growing entity. A0 is the initial amount or size of the growing entity at time t equal to 0. And A at t is the amount at time t, and k is a constant representing the growth rate. Now, if k is negative, less than 0, the function models the amount or size of a decaying entity. Again, A0 is the initial amount or size of the decaying entity at time t equals 0. A at t is the amount at time t, and k is a constant representing the decay rate. All right, so here's our first example. A culture of bacteria obeys the law of uninhibited growth. If n is the number of bacteria in the culture and t is the time in hours, express n as a function of t. So this one you got to stick in your brain. N at t equals n0 times e to the kt. So that's the general growth function using the notation with n. Now, if 500 bacteria are present initially and there are 800 after 1 hour, how many will be present in the culture after 5 hours? So basically, this phrase here, if 500 bacteria are present initially. So what does that tell us? Good, that tells us that N0 is equal to 500. Now, if you ever forget that, what you can do is you can evaluate N at 0 and you'll get the same result. You'll, you'll, um, you'll basically plug in, here, let's just do it. You would say, I'll do it up here. You would say N at 0 is equal to 500. So you would use that ordered pair and you would say 500 equals e to the k N0, times e to the k times 0, which would give you 500 equals N0 e to the 0, and e to the 0 is 1, so 500 would be N0. Or you can just recognize it from the general formula. So N0 is 500, right? So therefore, our function will be we're going to need to find K. That's our first goal. And we know N0 is 500, right? So that means so far we have N at T is equal to 500 times e to the kt. So find K using this information. The next information we've been given is there are 800 bacteria after 1 hour. So you've been given the ordered pair 1, 800. So we're going to use that information to find K. So N at 1 equals 800. So plugging that in, we have 800 is equal to 500 times e to the k times 1. So we divide both sides by 500 and we get 8/5, because the zeros divide out, is equal to e to the k. What do you think we should do next? Good. We need to evaluate the natural log of both sides, or apply the natural log to both sides of the equation. So natural log at 8/5 is equal to natural log of e to the k. So we'll have natural log at 8/5 is equal to k. So that's from the last section. So let's get an approximation for this. Go into our calculator. Natural log at 8 divided by 5 is approximately, so k is approximately 0.4700. Now our job is to answer this last question: how many bacteria will be present in the culture after 5 hours? So now we need to find n at 5. So now we have a new equation. We have an equation. We've been building on this. We now have an equation with k. So n at t is 500 times e to the 0.4700 times t. So n at 5 will be 500 e to the 0.4700 times 5. So now I'm just plugging in wherever I see a 5, I'm plugging in, or wherever I see a t, I'm plugging in a 5. That's what we do on this guy. Okay? All right, so here we go. And at 5 is approximately, so this, now we go to the calculator. We have 500 times e to the 0.4700 times 5. Enter. So we're going to have approximately, if we round to the nearest bacteria, we'll have approximately 5,243. 43. All right. How are we doing so far? Great. Okay. So the population of a Midwestern city follows the exponential law. If n is the population of the city and t is time in years, express n as a function of t. So again, what are we going to do? You got it. Good job. N at t is equal to n0 times e raised to the k times t. If the population doubled in size over an 18-month period and the current population is 20,000, what will the population be 2 years from now? 18-month period and the current population is 20,000. What will the population be 2 years from now? So, okay, let's see what we got. Again, we need to find k. So, we know that N0 is 20,000. So what is double 20,000? Good, 40,000. So we have basically an ordered pair of this k here is, we have to get it in years. So we'll have an ordered pair of 1.5 comma 40,000. Good. So we'll have an ordered pair of 1.5 comma 2 times 20,000 is 40,000. So let's do it. So we'll have 40,000 is equal to 20,000 times e raised to the k times 1.5. Good. Dividing both sides by 20,000, we'll get 2 is equal to e to the 1.5 times k. Now, let's evaluate the natural log of both sides, and we'll get natural log at 2 is equal to 1.5 times k. So we're evaluating the natural log at the natural exponential function. So that will just bring that exponent down. So Now what do we need to do? Perfect. Divide both sides by 1.5 to isolate the k. And we'll get k is approximately, so let's see what we have going on here. So we would have, be careful when you enter this kind of stuff in. You'll have natural log at 2. You have to end those parentheses and then divide it by 1.5. So we get approximately 0.4621. You want to carry out a lot of digits on these. And okay, so what have we found now? That we can rewrite our model with more information. So our model was n at t equals, well, we have 20,000 times e to the k, which is 0.4621, times t. So we are going to use that information to find n at 2. So n at 2 will be 20,000 times e to the 0.4621 times 2. I'll put that in parentheses. So going back to our calculator, we will get okay. And it looks like we'll have approximately 50,397 in the people in the population. I think it was people, yes. So n at 2 is approximately 50,397. All right, so next up, we've got a bird species is in danger of that's in danger of extinction, has a population that is decreasing exponentially. So 5 years ago, the population was at 1,400, and today only 1,000 of the birds are alive. Once that population drops below 100, the situation will be irreversible. When will this happen? All right, so let's see what's going on. We have this bird species, right? So we need to make a model for it, and we need to do the same stuff. What did we do? We found our initial population. We found our decay constant in this case, and then we're going to find out when the population will equal 100, and then that will give us information to answer the question. So let's do it. So why don't we do P for population, right? So let's just get some initial information. So we'll write our general model, okay? And in this, we'll find our initial population. So general model, it follows a decay property. We'll do P for population. Population at time t is equal to the initial population times e raised to the kt. So let's see. 5 years ago, the population was at 1,400. And today only 1,000 of the birds are alive. So let's consider the population 5 years ago as our initial population. So that's going to give us that P0 is good, 1,400, and that came from this statement. So what we'll have is P at time t is equal to 1,400 times e to the kt. See, it's already looking better, isn't it? Alrighty, so next up, we need to find k, right? So again, to find k, we're going to need to use given information. So in 5 years, what's happened to the population? Good. It's decreased to an amount of 1,000. So basically, we've been given the ordered pair 5, 1,000, where the time is in years. So let's do it. P at 5 equals 1,000. So we'll have the equation 1,000 equals P0, which is 1,400, times e to the k times, good, 5. It's 5. So dividing both sides by 1,400, we will have, let's see, I think this reduces down to, we can divide out those two, and then I think we're going to get 5/7. If we reduce it to lowest terms, equals e to the 5 times k. And then applying the natural log to both sides, we will have the natural log at 5/7 is equal to 5k. And then k will be approximately, let's see what we have here. So be careful on this guy. Oh, my bad. We have to divide both sides by 5 first, don't we? So when we do this, this is how we'll get it figured out. So we have the natural log at 5 divided by 7. Now close those parentheses, and then we're going to divide by 5. Good. So, good, we get a negative, which is one way to check yourself because it needs to be negative for it to be a decay function. So, negative 0.06729. Approximately. All right. Oh, I forgot my 0. Good. Okay, so now what model does that give us? We'll rewrite it at the top. So we'll have P0 is equal to 1,400 times e to the negative 0.06729 times t. Now we can find out when 100 birds will be left. So now we're using that last piece of the item. So 3, find P, find, let's see, find T when P at T equals 100. So setting P at T equal to 100, we get 100 is equal to P0, which is 1,400 e to the, and what was our k again? Our k was negative 0.06729 times t. So dividing both sides by 1400, we will get 1/14 is equal to e to the negative 0.06729 times t. And applying the natural log of both sides, we will get that t is approximately, oh wait, one more step. So natural log at 1/14 is equal to negative 0.06729 times t. And then we need to divide both sides by negative 0.06729. So let's see what we get for t. T will be approximately so we're going to do natural log of 1 divided by 14, close the parentheses, and then divide by negative 0.06729. All right, so we get 39.21. So basically, let's see, once the population drops below 100, the situation will be irreversible. When will this happen? So this will happen in approximately 39 years. We'll go to the nearest year. So let's answer the question, right? Let's do some sort of a conclusion. Actually, we have room down here. So for the situation will be irreversible in approximately 39 years. Okay? See, it's not so bad if you just cut it up into steps and you have your first step where you figure out what your equation should be, your general equation. Then you just need to recognize or find what your initial amount is, and then you need to find k, and then usually you have enough information to find out what, the ultimate item you wanted to find out. Okay, so here we go. A fossilized leaf contains 70% of its normal amount of carbon-14. So we want to find out how old the fossil is, and we've been given a half-life of, carbon-14, and that half-life is 5,700 years. So notice that we don't know what the initial amount is, right? But we do know the half-life of carbon-14. So this one, it's, a little weird, but you can do it. So here we go. So we want to write the general equation. So let's do A for amount, okay? So the amount at time t is the initial amount, which we don't know, times e to the kt. So now, believe it or not, we can go ahead and we can find K, even though we don't have the initial, because we have a relationship here. We're going to say, we're going to let A at 5,700 is the half of the life. So half of the life is 0.5 of the times the initial amount. Half of the initial. So let's do it. So A at T is half of the initial amount equals the initial amount times E raised to the K times 5,700. At time 5,700, you have half the initial. So look what happens. It's kind of groovy. You divide both sides by A0. So we actually could have done that population problem like this, but since we had the initial population, we just times it by 2. So here you get 0.5 is equal to E to the 5,700 times K, because these divide out to be 1, as do these. So then, applying the natural log to both sides, we will get natural log at 0.5 is equal to 5,700 times K, and then dividing both sides by 5,700, we'll get natural log of 0.5 divided by 5,700 is K. So K is approximately 'So in those parentheses, and then we'll divide by 5,700. Are we going to be looking for a positive or a negative? Good, a negative, because it's decaying. And there we go. So K is approximately negative 0. Now, e to the negative 4 means the decimal moves to the left 4 times. So we'll have 3 zeros in front of the 1. But let's carry out the 1, 2, 1, 6. So basically we'll have 0, 0, 0, 1, 2, 1, 6. Let me copy that for you. So that's what we did there in the calculator. All right, so, okay, so now we have K, right? So this now what we need to do is we need to find out how old the fossil is, okay? Now, again, we have been given that this leaf contains 70% of its normal amount of carbon-14. So we're going to find T when A at T is equal to 70% is 0.7, right? I'll put 0.7 times the initial amount. So here we go. We will have 0. So our general equation now, let's write it down first. So now A at T is A0 times E to the negative 0.0001216. That's what we found for K times T. So now we're going to let A at T be 0.7 times A0 is equal to A0 times e to the negative 0.0001216 times t. So do you see these a zeros are going to divide out. So applying the natural log to both sides, we'll get natural log of 0.7 is equal to natural log at e to the negative 0.0001216 times t. So that will give us natural log at 0.7 is negative 0.0001216 times t. And then dividing both sides to isolate t, we'll get natural log at 0.7 divided by negative 0.0001216 is equal to t. So let's see what we get on the calculator. So we have natural log at 0.7 in parentheses divided by negative 0.0001216, enter. So our fossil is approximately 2,933 years old. So t is approximately 2,933. So let's just write a quick conclusion. Sorry, it's low on space here. The fossil is approximately 2,933 years old. Okay? So that's our end result. So now let's look at a picture of this. So using your graphing calculator, graph the relation between the percentage of carbon-14 remaining in time. So basically, this is what we're going to do on our graphing calculator. We're going to say y1 equals e to the negative 0.0001216, and we're going to say times x, because on the older calculators it's just a lot easier to enter in x. If you have a newer one, you could keep t. I think it's easier to put whatever variable you want. So let's clear this, go to y equals. We'll clear these guys. All right, so here we go. So we have e raised to the negative 0.0001216 times x and we'll have to adjust the window. Let's adjust. Let's go y from like 0 to 1. See how that does. And let's extend x a bit more. Let's do an x max of 5,000. And we don't have to have the scale be 1. We can have that be 100. One more time. Window. Oh, the half-life is 5,700 years, so let's go further. Let's go to 15,000. There we go. Much more better. Sorry about that. Okay, so we had done the y from 0 to 1, and then we went to 15,000 on the x. So that's the relation between the percentage of carbon-14 remaining in time. So now let's use intersect to determine the time that elapses until half the carbon-14 remains. So we've already solved this problem, right? But now we're going about it from the other way. So basically, we're going to let y2 equal to 0.5. And then we'll use y2 is equal to 0.5, and then we can use intersect to find that result. So second, calculate intersect is 5. So the first curve is here. See how it jumps right to second curve? Hit enter, and then hit enter again, and you'll get the intersection. So just as we expected, right, because we were given this information at the beginning, we expected that this would be 5,700. Okay, so T is approximately 5,700 years. All right, and then let's verify our answer in part A. So what do you think we should do? What should we let y2 equal this time? Good, you got it. y2 should equal to 0.7. All right, so we were right, 2933. So we verified our result. Awesome. All right. So again, 1, 0, 15,000. So T is approximately 2,933. Check. Oh, in years. So we were right. Yay. Okay. So let's move on to our next one. Next up is Newton's law of cooling. So this is pretty cool. So for Newton's law of cooling, the temperature U of a heated object at a given time t can be modeled by this function. So U at time t is equal to T plus the quantity, the initial temperature, or I'm sorry, frickin' A. So U at T is equal to capital T. So capital T is different than lowercase t. Okay, so let's identify these things. So T is the constant temperature of the surrounding medium. U0 is the initial temperature of the heated object. And K is a negative constant because if it's cooling, it'll be decreasing. Okay, so let's do it. A thermometer reading 72 degrees is placed in a refrigerator where the temperature is a constant 38 degrees, and this is in Fahrenheit. So then we need to work with the model with the given information to figure out what K is. So yet again, we're going to find K, right? So let's rewrite our initial model. Okay, so we're going to write the general equation with the given information. Okay, so let's see what we've been given. So this thermostat, the initial temperature is 72 degrees. So U0 is 72. Now, the temperature of the refrigerator, the surrounding medium, is 78. So that's capital T, or 78, 38. Capital T is 38 degrees. So let's write our formula with that info and see what we've got. So U at T will be 38 plus 72 minus 38, and that's all times e to the kt, that parentheses. But I can certainly do 72 minus 38 inside the parentheses. So we'll get 38 plus, let's see, 72 minus 38. Oh, I can't talk anymore. Is going to be 34. So this will be plus 34 times e to the kt. Now be careful. Remember that multiplication comes before addition. So you cannot do anything with that 38 plus 34 e to the kt. So that'll be the model we're using. So second step will be, again, we need to find K. I bet you're getting tired of that. So here we go. The thermometer read 60 degrees Fahrenheit after 2 minutes. So we've been given the ordered pair 2, 60. So basically, what are we going to be using to find K? We're going to be using the fact that U at 2 is equal to 60. So here we go. We're going to say 60 is equal to 38 plus 34 times e to the k times 2. So we can take away 38 from both sides and we'll get, I think it's 22 is equal to 34 times e to the k, 2k. So dividing both sides by 34, and reducing, I think we get 11/17 is equal to e to the 2k. And applying the natural log to both sides, we have natural log at 11/17 is equal to 2k. And then dividing both sides by 2, we get k as approximately what do we have? 11 divided by 17. Close that the parentheses and then divide by 2. So we get approximately what? Negative 0.2177, we'll call it. So now what's our model? Our model is U at t is equal to 38 plus 34 times e to the negative 0.2177 times t. So finally, we can find the end result. So we need to find u at 7. So 7 is 38 plus 34 times e to the negative 0.2177 times 7. In our calculator, okay. Okay, so the temperature after 7 minutes will be approximately, we found, to be 45.4 degrees Fahrenheit. Okay, so let's see what part B is asking us. How long will it take before the thermometer reads 39 degrees Fahrenheit? So now we need to find time. So again, writing our general equation, we have 38 plus 34 times e to the negative 0.2177 times t. So now the information given is that u at t equals 39 degrees. So we need to find t. So we'll replace u at t with 39 and then we'll solve. So taking away 38 from both sides, we get 1 is equal to 34e times e to the negative 0.2177 times t. Dividing both sides by 34, we get 1/34 equals e to the negative 0.2177 times t. Applying the natural log to both sides, we'll get natural log of 1/34 is equal to negative 0.2177 times t. And then dividing both sides by 0.2177, we get natural log at 1/34 divided by negative 0.2177 is t, and t is approximately, so this t, remember, is time. Okay, so we have natural log of 1 divided by 34 divided by negative 0.2177. Enter. So in about 16.2 minutes, the thermometer will have a temperature of 39 degrees. All right. Okay, so let's take a look at what a picture of this would be. So we want to graph the relation between temperature and time. So our y1, this time will be 38 plus 34 times e to the negative 0.2177 times x. So let's take a look at our numbers. So our time, I want to get a better idea of the window so we don't have to mess around so much looking for the window. So our temperature starts at 72 and it's going to be going down to just to 38, right? Because that's the surrounding medium. So that'll give us an idea of our window. Okay, so there we go. Okay, so we had 38 plus 34 times e raised to the negative 0.2177 times x. And then our window minutes would go from maybe 0 to, we'll say 0 to 60, I guess. And the scale be 5. And then the y minimum, we can keep it 0, and the maximum, I'll put 75 because it started out as 72. Actually, you know what? The minimum temperature is going to be 38, so let's go to 35. And then we'll graph. There we go. That worked out much better, didn't it? All right. I'll take a screenshot. All right. Okay, so x we did from 0 to 60. Y, you know, maybe we should just do y from 0, you know, because I like writing the scale in. Let's see what it looks like. Let's see if we did 0. And we'll do this scale of 5 as well. Yeah, that way I can put the scale in, starting from 0 on both of them. All right, so this went from 0 to 75, and there you have it. Okay, so next up, we want to find out the time needed to elapse before the thermometer reads 45 degrees. So on this one, our Y2 is going to be 45. Graph. And then we'll go to intersect. And it's our first curve, second curve, enter. And this is our result. So, again, this is from 0 to 75, and that goes to 60 on the T. So, time needed to elapse before the thermometer reads 45 degrees. The thermometer will read. Thermometer. -45 degrees after approximately how many minutes? Approximately 7.3 minutes have elapsed. Okay. And lastly, trace the function for large values of time. What do we notice about the temperature? So let's go to trace. And to get to large values of time, we cursor to the right. So what are you noticing? What's happening? Getting pretty close to what? What do you notice in 38 degrees, right? And doesn't that make sense? Because the temperature's at 38 degrees in the refrigerator. So we can say, again, this is 0 to 60 and 0 to 75. We could say as the time approaches infinity, the temperature approaches the temperature of the surrounding medium, which was 38 degrees Fahrenheit. All right. So next up, the logistic model. All right, so this will be our last model that we talk about. So the logistic model, it also can have, a growth or decay trend, but it's limited growth or limited decay. So the easiest way to picture it is, imagine you have a fish tank, right? Um, I mean, isn't there a limited number of fish that can survive in the fish tank before they start dying off, right? You can't jam in 5,000 fish into a fish tank. So, I mean, a regular size fish tank. So, so a logistic model helps makes adjustments for that. So the general form of the logistic model is P at t equals population at time t equals C, which is the carrying capacity, divided by the quantity 1 plus A times e to the negative bt. So A, B, and C are constants with A greater than 0 and C greater than 0. The model is a growth model if B is greater than 0, because see, there's a negative in the formula. And so you just look at what exactly is B. The model is a decay model if B is less than 0. So I know that looks a little strange, but you have e to a negative exponent in the denominator. And so that is why that is why we have why it'll behave in that way. Okay, so just a couple of pictures. Population size, carrying capacity, time. So the first one, you've got early growth is rapid, like these little areas are saying, and then the growth begins to slow at some point. So here, where the graph changes, do you see how it's kind of curving upward here? And then at this, where they change colors in the graph, it now it's curving downward, and then it levels off, right? So so that is, an example. This one I thought was kind of cool. I was just searching the net, and this is where you can use data to model. You can actually get an equation from data. So this one here, do you see early growth, right? And then early rapid growth, and then it changes and levels off, right? And this guy over here, again, you've got sort of a logistic going on, right? It's really clear on the blue. Okay, so here's the properties of the logistic model. The domain is the set of all real numbers. Oops, need the pen back. The range is the interval from 0 to C, where C is the carrying capacity. There are no x-intercepts. The y-intercept, it's complicated to remember, so just remember that it's going to be p at time 0, and you evaluate that. There are 2 horizontal asymptotes. Y equals 0 and y equal to the carrying capacity C. And P at t is an increasing function if B is greater than 0, and a decreasing function if B is less than 0. There is an inflection point that we talked about, where P at t equals half the carrying capacity. The inflection point is the point on the graph where the graph changes from being curved upward to downward, and that would be for growth functions. And the point where the graph changes from being curved downward to upward. For decay functions. Okay. Let's do a problem. Our last one of the lesson. All right. And we're going to be done with chapter 5 after this one. Often environmentalists capture an endangered species and transport the species to a controlled environment where the species can produce offspring and regenerate its population. Suppose that 6 American bald eagles are captured, transported to Montana, and set free. Based on experience, the environmentalists expect the population to grow according to this logistic model here. where T is measured in years. So determine the carrying capacity of the environment, right? Well, in calculus, we're going to take a look at what happens as T approaches infinity, as time approaches infinity. So what do you think? I mean, look at this one here. As T approaches infinity, what's going to happen to that exponential? Isn't it going to get very, very, very small, very close to zero because of the negative coefficient? So if that gets close to zero, 0 times 82.33 is 0. So P at T would be approaching 500 divided by 1, which is 500. So the carrying capacity of the environment is 500 bald eagles. Or as long as you have the the equation written exactly in this format, you can just see that our C right here is 500. Whoops. Okay. So, and that's from up here, just to let you know, our logistic model. Actually, let's rewrite the general model so you have it. Okay. So here we go. We'd have, so our general model is P at T is equal to C divided by 1 plus A times E to the negative B times T. Okay. So as you can see, C is here. All right. So now we need to find the growth rate of the bald eagle. So what do you think? What is the growth rate was B, wasn't it? So what would you say the growth rate is? So here we're looking for what corresponds in the general model. So do you see that B is right here? So B is positive. It's positive because the sign on the logistic model is negative. If B was negative, it would have turned positive because that negative is in the formula. So the growth rate, so B is negative, or not negative, B is 0.162. So in a percentage, the growth rate is 16.2%. All right. Use a graphing calculator to graph. So let's get our formula up. All right, so we have 500 divided by, you got to put parentheses around it, otherwise it'll only divide it by 1. So we have 1 plus 82.33 times E raised to the negative 0.162, and we'll do times X. Now our window, let's think about our window. So let's, not sure about time. I am sure about the window for, let's do, let's keep it as x from, let's try 0 to 30, okay? And see how that goes. And then for the y, go 0 to 510 because the carrying capacity is 500, so it's not going to exceed that. So let's see what that looks like. Okay, I need to increase the time because it hasn't attained the carrying capacity yet. So let's go 0 to 100, and I'll change the scale to go by 5. Oh, nice. Okay. I like the graph of the logistic model. I know I'm dorky. All right. So here's our model. And then put our scale in. So we went from 0 to 100, and we went from 0 to, what did I say, 510? So now, what is the population after 3 years, right? So here, after 3 years, what are we doing? What do we have to do? Good. We have to go to second, calculate value, and we enter in x is 3. Okay, so we're evaluating the logistic function when our time is 3. So the population would be, no, I'm not sure. I mean, usually on these things, you know, we don't want to consider part of an eagle, right? So we'll say approximately 10 eagles, approximately 10. All right. So approximately 10 bald eagles. And then when will the population be 300 bald eagles? Well, how do we do it then? Great, we need to do an intersect deal again. So we go to our y equals, and we go down to y2, and we say 300 and graph. And then second, calculate, intersect, first curve, where is it? There we go. And view, so enter, 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 and we get this result. So again, same scale. So we have our intersection at, we can do partial time. So in approximately 29.7 years. we'll have 300 bald eagles. All right, so how long does it take the population to reach half of the carrying capacity? Well, half of C is half of, good, 500, because that was our carrying capacity, which is 250. Right? So what other information is this going to give us? Awesome, it's going to give us the inflection point, So let's do it. So we're going to do y2, this time will be 250. All right, so we're going to go to second, calculate, intersect. So we can see it. So enter, enter, enter. All right, so pretty close to what we had before, right? We had, before we got 29.7, and this time we got 29.2. So takes approximately 27.2 years to reach half of the carrying capacity. All right, so we're done for today. We're done with chapter 5. So you guys have a fabulous day, and I will be talking to you soon. Bye.